Okay, this is Data Structures in C. This is Computer Science 2 course. Um, let's talk first about the prerequisites. Oh, I'm Brian, by the way, so I'm going to be the one who's going through these slides with you and for the remainder of the courses. Okay, so prerequisites. This assumes that you've got some exposure to programming already, preferably Computer Science 1 class or similar. Um, it would be great if that class was in C. Uh, if not, then it does assume that you've got some other familiarity with C, that you've seen some C syntax before. I may do an introduction to computer science and C class at some point, but I haven't done that yet. So if I do, I'll put an update in the comments or something here. Use of dynamic memory in C is required for this course. There are situations where data structures do not use dynamic memory, but most of the time they do. We will be making use of it. And I'm going to have a review of how to use dynamic memory in C as a separate lesson. In fact, it will be the next one that is in this series. So um, never fear, if your introduction to C course, didn't cover that. I know some don't. We will cover that. And if you have, then, you're feel free to use that as a refresher. Why C? There's so many languages these days that, either already have data structures in them or, which you could think of as, being more oriented towards making data structures? Well, a lot of reasons. C is kind of the Latin of a lot of modern programming languages. You see I've listed, several here that are all descendants of C syntax. The first three there, C++, Objective-C, and C Sharp, they all extend C's functionality literally. The rest of them just kind of inherit the general structure. Um, it's just a common way to write languages these days. And so having an understanding of how to do this in C, um, it will translate somewhat, into other things. Um, the core of all major operating systems these days, are also written in C. Uh, all versions of Unix, including Mac OS, Windows, Linux, Android, which is a Linux derivative, they're all, C at the core. With what's called the kernel of those systems is all written in C. So if you ever get into operating systems or find yourself interacting with the kernel of those systems, you're going to be looking at using C to do that. All of these systems use data structures in some way internally. So their data structures are written in C. If you ever do have to get into, actually doing, say, Linux kernel development or something, um, you're going to have to understand how to do this with, just plain regular C. C is often the first high-level language available on a new processor. This is especially true on embedded processors. So if your work takes you into the realm of working on embedded development, then you really need to be able to use C effectively to do your job. Um, and not everything here is going to be a one-to-one translation for all circumstances you're ever going to come into contact with over the course of your career. But having the basic foundation of how to do this, you know, any of these kinds of environments, it's going to be helpful. It's going to be useful. So it's a good foundation to have. So what is a data structure? What do we mean when we're talking about a data structure? Well, a data structure is a way to store more than one element of related data together. Things like a list of groceries, names and grades of students, deposits and withdrawals from a bank account. These are kinds of things that you may have seen in your introduction to C course. Um, all very common. And it's just, we could go on ad nauseum about, different ways to, different things we want to group together that are related. Simplest way to do this is an array. In C, that can be a static array declared as a local variable or a global variable, or it can be something that is declared with dynamic memory, which is something that we're going to be doing in some of these exercises. Um, Everything in an array is just addressed by index. You start at 0, you go upwards from there. And C, this is the only data structure that C natively supports is an array. So anything beyond that, anything more advanced or any other way to access information, we need something else. Okay, why would you need something else? Um, when you don't know how many things you're going to need up front, okay, you can resize arrays, and in fact, we're going to be doing that in some of our lessons here, just as examples for how that is done. But it is slow for the operating system to do that. Um, it takes time, and there's some gotchas around doing that. You have to be careful when you do that. So it's always better to declare the array the size that you need it to be up front when you can, and if you don't, then maybe an array isn't the right tool. Maybe you need a different tool for that. Um, Another is when you want to look up something by something other than an index, right? In an array, all you have is a number, 0 through whatever. If you are storing information about a person, you probably don't want to look up by index. You probably want to look up by name, the name of the person and the information associated with that person. You can do this with just using arrays by themselves, but you'd have to keep track of multiple arrays to do it. And that is error prone. When you have to invent things like this yourself and keep track of multiple pieces of information yourself, um, you tend to make mistakes. It's really much better if you can have just kind of a common standard way of doing this and just use something that is meant to do this from the beginning. Another reason you need something else is when you need to find information quickly. If you have a normal unsorted array, in order to find what you need, you have to start from the beginning and examine each thing along the way until you find what you're looking for. In real world situations, this is often too slow. We can do it. We do it a lot. It's called a linear search. But data structures allow us to organize information better, so that we can find things more quickly. And so when you need to find something better than just starting at the beginning and going to the end or until you find it, data structures provide other ways of doing that, or of organizing information so you could do that more quickly. All right, so we're going to cover multiple different kinds of data structures over the course uh, of this course. Um, how do we make decisions about these things? How do we compare them to each other and decide when we would use one versus the other? Well, we evaluate them by what's called the time complexity of their operations. So basic operations are getting an item from it, setting an item in it, adding an item to it, and deleting an item from it. And we say that the time complexity of an operation is a certain order of n, where n is the number of elements that it holds. So we express this, big O parenthesis x in parenthesis, where x is some expression that relates to the value of n. So when we're talking about an unordered array, for example, unsorted array, uh, searching or getting an arbitrary item out of the array would be order n, because the number of comparisons that we need to make scales directly with the number of elements in the array. So if we have an array that's 50 items in size, on average we're going to do 25 comparisons because what we're looking for is going to be somewhere in the middle. If we have an array that's 100 items in size, then on average we're going to do 50 comparisons. So the number of comparisons that we make on average scales one to one with the number of or not one to one, but scales linearly with the number of items that are in the array. Um, However, assuming that your array is already large enough to hold more items, then adding an element to an unsorted array is just order one, or we also call that constant time, because it just requires setting the next value and then incrementing the number of values that you have in there. So it is the same uh, number of operations every time you do it. Set the value increment. That's it. It's basically one operation. Deleting a value from an array, though, is back to order n because we have to copy from wherever that item was in the array to the end of the array. And so on average, again, when you're looking for is going to be somewhere in the middle. So an array of 50 items, you're going to wind up doing 25 copies because your item is somewhere in the middle and you have to copy from the middle of your array all the way to the end. Um, but assuming that you already know where your item in the array is, then setting the value is going to be another order one because arrays you look up by index, you already know the index, you just set it, that's it, that's all you have to do. So that's constant time again. Okay, data ordering. So different data structures order data differently internally, and sometimes that makes a difference. So we're going to talk about the use cases for different data structures as we go through this. And sometimes the data that they're using internally matters in terms of how we use it. So some data structures maintain the order, the order that you add them in is the order that you're going to get them out. Okay. Um, some of them maintain data in sorted order. So if you add things, uh, you know, 5, 3, 1, 4, 2, you get them out 1, 2, 3, 4, 5, always. Um, doesn't matter, which order you add them in, you're always going to get them in sorted order. Some of them maintain data in a semi-random order because some of these data structures work on principles of even distribution of data. And that tends to make the way that they look in memory random. It's not strictly random, but it can look that way when you're going through it from beginning to end. And so if you don't care about whether or not your data is random, maybe that's fine. But if you do care, then which one you use here makes a difference. So there is no one size fits all here. There is no one data structure that works, you know, in all cases the best. And so how you're going to use it in your program affects the choice of the data structure that you're going to use. So just bear in mind there are differences and you need to think about how you're going to be using this in real life when you make a decision about which one to use. Okay, iterating. In addition to getting just any arbitrary element that we want out of a data structure, all data structures support traversing from beginning to end. You start at the start, you go to the end, you get through each individual one. There's different reasons why you would want to do this, but basically anytime you want to, examine uh, all of the elements of a data structure, you need some way to do this. So this is accomplished by something called an iterator um, that is dedicated to the type of data structure. So there, each individual type of data structure is going to have its own um, unique iterator that understands the internal mechanisms of that data structure and can go through one by one. Incrementing the data structure, the iterator prepares it to provide the next value in the data structure. The increment function destroys the iterator and returns null once there are no more elements to provide. So this goes back to data dynamic memory. So our iterator is going to use dynamic memory. We're going to create it, um, go through every value that it holds, and then at the end it's going to destroy itself and return null back to us. Anytime you access the current value of the iterator, it returns whatever it is currently assigned to within the data structure. So you access the value, it gets its current value, it returns that back to you. So basically that means there's two functions for an iterator. One is initialize, three. Create, so initialize, uh, go to the next one, and then get the current value. So three basic operations of an iterator. Everything that we're going to talk about is going to have one of these. I'll walk you through what this means and how to create one in real life. Okay, that's it. So, hope you found this informative. If this sounds like something you're interested in, then by all means keep watching the rest of these videos. I'm gonna put links to the GitHub repository that has all the information, all the slides, and all the example content in the comments of these sections as we go through. Next up is going to be a refresher on dynamic memory, and so I'll see you there.